Welcome to the CausalBench tutorial. Today's tutorial will be on how can use CausalBench to streamline your causal learning research, and we'll also be having a hands-on session where we'll go over how you can upload your resources to CausalBench and use CausalBench to run experiments. Before I proceed, I want to acknowledge various grants provided by the National Science Foundation and the US Army Corps of Engineers, without which this research would not have been possible. I would like to introduce the team. I'm Abhinav. I'm here with Pratanu, Ahmet, and Dr. Hwan Liu. And we have four other teammates without whom this project would not have been possible. So, without further ado, I'd like to go to the main topic. So, what is CausalBench? CausalBench is basically a benchmarking platform for causal learning research. We cater to the unique needs of causal learning community, and we have four main goals. The first is to promote universal adoption of standard data sets, metrics, and procedures for causal learning. We also want to facilitate collaboration in our community and promote trustable and reproducible benchmarking. We also want to promote fair and flexible comparison of models. And to do this, we are going to demonstrate scenarios which we think a causal bench has to achieve all of these four goals. Let's look at some scenarios where you might use causal bench and how it can achieve each of the four goals I just discussed. So the first use case you might have is you might have some data models or even metrics that you want to introduce to the causal learning community. So this is when CausalBench comes in. CausalBench can be used as a platform to share your data sets, models, and metrics related to causal learning research with the community. Now, how CausalBench is advantageous in this aspect is that CausalBench allows you to have different versions of the same resource and also public and private versions. So even if you upload your data to our servers, it doesn't have to be visible to everyone on CausalBench. You can keep your data to yourself. And apart from this, CausalBench also allows you to modify, create a clone and modify others' resources. That way, we are keeping the doors open to everyone in the community to improve resources that are available to us. And moving on to the next scenario, you might not have resources to contribute, but you might be looking for resources to use in your own research. In such a case, a CausalBench provides powerful filters and search options to efficiently filter through the resources that are available on our website and find the resources that suit your needs. And we also record important information like the number of experiments that were run using these resources, the number of experiments run using each dataset, model, and metric, and the number of downloads that each of them have, which I think would guide any user in making a more informed decision. And such a user could be an ML researcher who is looking for new data sets to test their model on, or this might be someone who is looking to explore the research field and they want to learn about new models that they can compare against, that they can include in their study. And it could also be someone who is looking for a fair metric to compare all the models in their study. Or let's say you want to run experiments. This is where the benchmark executor comes in. So a benchmark executor essentially runs a benchmark context which orchestrates the experiments. So before we move further into scenario 3, I would like to go over what a benchmark context is. So a benchmark context has 5 components. The first one being task. Task essentially connects the data sets with models and the models with metrics. And it orchestrates how the data flows within the benchmark context. So in causal learning, the tasks can be of many types. Broadly speaking, it can be causal discovery or cause effect estimation. Um, in causal discovery can also be of many types. One being static causal discovery and the other being temporal causal discovery. CausalBench actually supports both of them right now, and we are planning to introduce more in the future. And after task, that's where the data sets, models, and metrics come in. So these are essentially, so how a benchmark context works is each model is trained on every data set. So you have n by m trained models, and these n by m trained models are evaluated on all the k metrics. So in this scenario, each data set model and all the k metrics, they constitute a benchmark scenario. And when all of these scenarios are run, that's when a benchmark run gets generated. And if I were to talk about the fifth component of benchmark context, which is the hyperparameters, which is again pretty much self-explanatory, but I would like to point out that in causal learning, sometimes even the metrics might have hyperparameters. With that, I'll continue with our scenario 3. So a benchmark executor could be an ML researcher or a domain scientist who is looking to compare a number of models with trained upon a number of data sets, and they want to study how they perform. So that's when they execute a benchmark. Or it could even be someone who is going through a research work and they want to replicate experiments which are presented in the research work. So replicating experiments using CausalBench is as simple as just getting the context ID and the version number and running it on your computer. Everything else is being orchestrated by the CausalBench package, so you don't have to worry about cleaning the data or connecting the data sets to the models or connecting the model output to the metrics. Everything else is being orchestrated by the CausalBench package. Shown on the screen are the outputs of a benchmark context execution. On the left, you can see the hardware profiling information. We also profile software data. This includes Python versions, the imports that are being used by the models, and metric files. So we profile information like memory usage, which is shown on the screen, memory usage by the model, the disk that the model is using, and the number of read bytes and the write bytes that the model is performing. And every benchmark run that is published onto CausalBench and made public is also pushed to Zenodo. And Zenodo is a DOI provider which indexes documents. This gives you a DOI that you can cite in your work, and which basically makes things easier when you want to present results or link results into your research. You might not want to execute benchmarks or contribute or even explore, but you might want to explore the field, see what the current state of the art is, see what is affecting the performance of the models most. Is it the hardware? Is it the hyperparameter settings? What is it? So in such a case, this is when you want to explore the benchmarks, the benchmark runs. So such a user could be again an ML researcher or a domain scientist. For the benchmark explorer, we have again a lot of features which we'll go over in the hands-on session. So we first provide filters which the benchmark explorer can use to filter through various runs. And once they do that, they can run a causal explanation to to find the cause-effect relationships between the experiment settings and the experiment output. So this could be like the effect of hyperparameters on the accuracy metric, for example. And we also, once the causal analysis is run and the cause-effect relationships are ascertained, we also provide recommendations to the user, which we think could strengthen the causal analysis. I'll go over a quick example on where causal analysis could be useful. So on the screen, I have two results. Both were run using Warlinger model, but on different datasets, which resulted in different accuracies, very different accuracies, and very different runtimes. So when we have such diverse results, we obviously get a few questions. So we think if the hyperparameters played a role in the different accuracies, or is it because of, or is the time is the runtime increasing because of the increase in dataset size, or is there anything else that is affecting both of these? So these kinds of questions can be answered using the causal explanation module. On the left side of the screen is the UI for the causal explanation module. This is where you select the effect variable that you want to analyze, and below that is the ranges for the hyperparameters which are essentially either integers or floats. These ranges are used to recommend the experiment settings after the analysis is done. And on the right, we have a sample causal explanation report that we generated to explain the questions we presented on this slide. So we can see that in the experiments that in the results that we showed, we see that model memory and model write bytes have the highest impact on time duration, which kind of explains the reason why the time duration is increasing. It's probably because the data set size is much larger for the second data set compared to the first one. But in some cases, causal explanation might contradict our hypotheses. Now that we have we have had a deep dive into CausalBench, I'd like to zoom out a little bit and go over the components of CausalBench. So CausalBench contains three main components, them being the backend server, the front-end server, and the Python package. The Python package handles everything that runs on your system. It clones the datasets, models, metrics, and the context that needs to be run, and it orchestrates the experiment on your machine using the benchmark context. And once the experiment is run, it also handles uploading to the backend, uploading all the results to the backend server. And while the experiment is being run, it ensures it ensures profiling of hardware and software information, like as I said before, the versions of the software that is being used, like the Python version and the versions of the packages, and also the hardware details, like what exact CPU is it being run on, what is the GPU version, what is the GPU driver version, and so on. The web backend handles the requests sent by the package, handles uploading files, interacting with the Zenodo API to generate DOIs. And the web frontend provides a GUI for users to browse benchmark runs, datasets, models that are already published to CausalBench. You can also upload resources through the UI, but you still have to package it as a zip file, as you would have done with a CausalBench package. With that, we come to an end on the CausalBench, on introduction to CausalBench. I would like to go over today's agenda before we go on to the next part. So we started off with a introduction to the tutorial and CausalBench. We'll move on to a brief introduction on causality and causal learning. And then we'll deep dive into the CausalBench framework to create and execute benchmarks, which will be followed by coffee break. And then we'll have a shorter introduction to CausalBench and causality. After that, we'll explore already published benchmarks and benchmark contexts, which are published by different users on CausalBench. And we'll see how you can reproduce experiments using CausalBench. After that, we'll gain further insights and analyze experiments using the causal explanation and recommendation module. And we'll conclude with our future works, what we have plans in the future for CausalBench. With that, I'd like to open the stage for questions. Any questions? I don't think we have any questions. I'll pass over the mic to Ahmet, who will go over the causality section of the tutorial.
All right, thank you, Abhinav. To make the most of a CausalBench, we have to understand the underlying system, which is causality. Because CausalBench is a tool designed to help us execute causality tasks or causal learning tasks. And as it goes in the name, most of CausalBench is based on causality. This section will provide a brief overview on what causality is, why does it matter, and two tasks in causal learning and how CausalBench utilizes or handles them. Causal learning has been growing steadily, and the interest in the field has almost doubled in the last 3 years. So it is quite a hot topic, and there have been more and more works published in that. KDD takes its share from that as well. Alright, why does something happen? This is the question causality seeks the answer to, by describing the relationship between a cause and its effects. When we think of a scenario in our heads, like what would happen if we did X, or estimating the probability of doing Y, we actually apply causality in real life. We imagine a system with a set of implicit rules and simulate different scenarios. And causal learning is the systematic approach for computers to assist us in answering the question why through two major tasks: causal discovery and causal effect estimation. So what are these tasks? When we have a set of observations on a number of variables and we want to learn the causal relationship structure between those variables to understand if two variables affect each other, we utilize causal discovery. And when we know the causal relationships between variables, but we want to quantify the effects between these relationships, we apply causal effect estimation. So why does causal learning matter? Why do we have a need to use this? To answer this question, we need to look at what happened before, the existing approaches that try to answer the question why. Up until now, we have used traditional data analysis approaches, machine learning or different statistical approaches. And they relied on statistical or probabilistical approaches to understand data. For example, let's take the dimensionality reduction problem. We have some data with a number of variables, and we'd like to eliminate the redundancies to process data more efficiently. But how do we really decide what is redundant or not? Or how does the removed variable affect the system? Do we change the latent component that is created a combination of features? With the regular approaches, we have tested it with the more experimental methods, which had their own difficulties. So to answer that question in the field, we have a wide spectrum of methods with different complication spreadsheets. For example, PCA helps us remove the redundancies by matrix decomposition, but it can remove the variables based on just some correlation. Or another example is deep neural networks. It also can be used to help remove redundancies, but the problem is we do not learn any insights from a neural network. Yes, it provides us with some results, but it does not tell us why is it useful or why is it not useful. It is essentially a black box. So, just observing the correlation or the combined components as a whole does not make sense in data science. For instance, the story that we can see in this graph is that with vaccination, mortality also increases, which is a different scenario. But when we look at the data carefully, for example, when we divide them by age or notice the groups that exist in the observation, we can say that taking age into factor tells us an entirely different story. Here, we can see that vaccination actually decreases the chances of mortality. Or in causality terms, we call age a confounding variable that affects both mortality and vaccine. If we do not account for the confounding variables, we risk making wrong conclusions. And that is the part where the regular approaches fall short. Alright, there are three main questions that causal learning seeks answers to. One, can we obtain causal knowledge from observations and answer causal queries based on those observations, which is causal discovery. Question 2, can we compute the probability distribution of a variable after we intervene on another, which is denoted as the do operator? This is the causal effect estimation. And 3, if we are given a prior causal knowledge, how do we utilize it in real life or data science questions? How do we use the insights that we gain from question 1 and 2 into practice? Alright, for this we have to learn how does the world or how does the current state of the art understands the causal relationships and which causal model frameworks comes into play. A causal model helps us to understand how variables influence each other or make predictions under interventions and going beyond the simple questions, simple observations to answer why and what if questions. And there are multiple ways to perceive a causal environment. So we have different causal models, each to their own goals. For example, Pearl's causal model is one of the most known causal models. It is being widely used in computer science. Rubin's causal model is popular in statistics and econometrics as well, but each to their own tasks. Speaking of causal algorithms, we provide a quick taxonomy on the algorithm types of causal learning. As there are more than a single way to perceive a causal environment, there is also more than a single way to achieve these causal tasks. For example, on causal discovery, some algorithms work by creating constraints. Some find the graph by using scores, utilizing some functions, or optimization based. As the nature of data changes, the discovery method also has to change. For example, with the static and temporal data, the dynamics, the cause-effect dynamics are also different. So temporal models have their own place. And the highlights algorithm on this part are actually supported by CausalBench out of the box, meaning you can directly use them. Or you can implement yourselves as well. For causal effect estimation, when we aim to quantify the effects, we also have a number of different approaches: regression-based, matching, IPW, causal force, or double machine learning. And we also utilized effect estimation models in CausalBench as well, but not as a direct algorithm at this point. We utilized effect estimation in our causal explanation model to assist you in finding why did we get the benchmark results. Alright, we have mentioned the causal graphs earlier. Now we will learn what they are and how do they work by explaining Pearl's causal model or DAGs and with key concepts in causal graphs. One of the core ideas on the Pearl's model is the directed acyclic graph, DAG representation. For those of you who are new to the graphs by any chance, a DAG consists of a set of variables which are represented as nodes, and a set of edges between these variables. Let's go over this example to further understand the causal graph. First part, nodes and edges. Here we have a causal graph of several effects over GPA. The nodes are socioeconomic status, nutrition, study time, sleep, and GPA. The shown set of edges represents the relationships between these variables. For example, we can say that study has a direct effect over GPA, and socioeconomic status has an indirect effect on GPA. Okay, when we are talking about causal graphs, we also have to discuss what structures can be observed in a causal graph and how do they affect our observations. First of our example is a mediator structure. In this example, sleep causes waking up time, and waking up time affects arrival time at work. And we also provide some data distributions at the graphs below. At the bottom, you can see the relationship between A, B, C, and in a mediator structure, you can observe that all variables depend on each other. B is correlated with A, B is correlated with C, and C is also correlated with A. Our arrival time at work depends on our sleep time. Another structure is a fork, or a common cause. Here, with taking the example of vaccine and mortality, we can claim that all variables depend on each other, meaning that vaccine is dependent on age, vaccine is dependent on mortality, mortality is also dependent on vaccination as well. And the last structure you can observe in a causal graph is a collider, where multiple variables have an effect over a single variable. In this example, good looking and being good looking and acting ability have an effect on getting awards. However, the difference is that, as you can see from observations A and C, good looking does not have an effect on acting ability. The distribution is independent. Here is a quick summary of how a graph structure itself affects the data independencies. In all of these examples, A and C are not directly connected, but we are able to make comments based on the graph structure and our observations. The question is, what if we wanted to observe the direct relationship between A and C? Because, as you can see here, B has been a common cause between all of these paths. For that, we utilize conditioning. Conditioning is where we set a fixed value for the common node, which B in this example, which allows us to observe direct relationship between A and C. Because since B is going to be the same, the only thing that we can observe is how A acts with C. And it is called conditional independence, when two variables C and A are conditional independent given a fixed value of B. Alright, the question is, how does conditioning on B change A and C in the structures that we have just discussed? Looking back at our examples, even though there is a causal relationship between A and C, when we fix the value on B, we will see that A and C appear independent from each other. It changes how we observe the variables. For fork, the same applies as well. When we fix by the value of B, we remove the correlation and observe that A and C are independent from each other. However, on the collider example that we had, the good looking, awards, and acting ability, the opposite happens. Conditioning on B has created a negative correlation between A and C. If you remember the example, you will also observe an issue that conditioning brings. Because by conditioning, we are essentially saying that good-looking actors cannot act, which is a spurious correlation. So it's a tool that is good only if used correctly. And now we can also understand how does conditioning on a variable affect how we observe the data. Okay, now we know about conditioning. Let's learn about how can we use this to affect or work on more complex causal graphs. I will not go into much detail, but a path in a causal graph is blocked if 1. The path contains a chain or fork that has been conditioned, meaning that we cannot make an assumption between x and y in this example. Because conditioning erases the evidence of the underlying causal relationships. It is blocking you from making causal assumptions between those variables. And it is blocked if the path contains a collider and the collision node and its descendants have not been conditioned. Because in this case, conditioning unblocks the path at the cost of introducing spurious correlations. So yes, when you apply conditioning, you can actually make some causal assumptions, but that will introduce some spurious correlations. So there's a risk to it. Alright, in such a graph, x and y are d-separated given z, if all paths from x to y through z are blocked. This is called d-separation. Alright, with a brief introduction on the causal graph structures, let's learn how to discover them using causal discovery. With causal models, we have learned how to represent the causal knowledge. The next question is, where do we get the knowledge itself from? There are two options for this. One, either an expert provides us the knowledge, meaning that we have to contact an expert, they have to look at our data, they need to have a level of experience, and then create a causal graph that answers our question, which is rare and expensive. And it might also prone to failure. You cannot avoid potential failure. And two, the alternative is we learn it from observations, which causal discovery aims to solve. Unlike the domain experts, the cost of having a better algorithm is far more cheaper than hiring a better consultant. And another practical reason why there is a need for causal discovery. Alright, so how does causal discovery work? Similar to machine learning algorithms, we start with a series of observations, and we aim to discover a set of causal relationships within the variables. And these relationships does not necessarily have to constitute a single graph that includes all the variables. We can end up with multiple separate causal graphs as well. However, the nature of data affects how do we apply causal discovery. If the observations are temporal, we will have to rely on whether we can use a variable to predict another one. In case the observations are static, meaning there is no time to it, then we should apply conditioning, which we have just learned, on the variables to discover what statistical independencies that we can learn. For the purpose of this tutorial, as these methods take much longer to execute, we will only focus on the static counterparts. So we will use static causal discovery during our hands-on part. To help us do the causal discovery, we need to have a set of assumptions in causal discovery. And one of them is called the Markov condition, which is the assumption that a variable is independent from the variables, that it has no edge in between. So there is no unknowns. Faithfulness is the causal graph structure given a d-separation, is also reflected in data distribution, meaning the data and the graph does not contradict each other. And lastly, sufficiency states that all common causes are included in the data. However, even under the previous assumptions, conditional independence tests may not be sufficient to distinguish different causal graphs. For example, let's take the example on the right. Causal graphs 1, 3, and 4 have the same conditional independence structure. X is dependent on Z, and X is independent from Z only given Y. But when you look at causal graph structure 2, you will see a different story. X is independent from Z, and X becomes dependent on Z when we conditional y. And we call this similarity between 1, 3, and 4 the same Markov equivalence class, meaning the nature of them are same. Alright, now let's learn about a simple causal discovery algorithm to solidify our knowledge. PC algorithm is an easy algorithm to explain within our given time. The key idea in PC algorithm is that it uses conditional independence tests, static, to infer a graph structure from a set of observations. And to this, when we are running any kind of an algorithm, we should also ideally have a ground truth graph to compare it against after our algorithm is complete. The first step of PC algorithm starts with a fully connected undirected graph. And then by conditioning through every possible set sizes, the algorithm fetches through every edge between two variables for a set that they can render these two variables, any selected variables, statistically independent. We are trying to find statistical independencies. If there is such a set, then we remove the edge from the graph. So we remove it. And this results in an undirected causal skeleton. The next part is we have to add the edges. Because as you know, directed causal graphs means there should be direct acyclic graphs means there should be directed. So the next step, this undirected causal skeleton is converted into a direct causal graph by orienting the remaining edges based on collider rules. And that is, for each pair of non-neighbors, let's call them x and y, which share common neighbor z. If z is not in separator set for x and y, that means z is a collider, which also gives us two directed edges in this case, x to z and y to z. So now, we are able to discover a causal graph using a causal discovery algorithm. But how do we evaluate the performance of a graph discovery algorithm? Or how do we even represent a graph that allows evaluation? As I said before, we need a ground truth graph to compare our discovery graph against. Then we need a way to compare these graphs. This is where adjacency matrices comes into help. It is one of the most common and simple ways to encode a direct acyclic graph. For those who are not familiar with graph theory, the idea is to create just an end-to-end matrix where all potential tuples of variables can be represented. We use a 1 to denote if there is an edge, and 0 if there isn't. And by representing a causal graph in form of an adjacency matrix, we can also apply different common metrics that we have utilized through classification algorithms. For example, precision, recall, F1, and more. Or structured having distance is one of the examples as well. But to understand or make the most of the graph or causal structure, we can also quantify the intervention behavior of two graphs to create an evaluation metric which is more relevant. So how does intervention behavior works is that by observing node pairs on the example on the right, we can find two more node pairs in the ground truth, which denotes the structural intervention distance, so that we have two comparable graphs. In this example, there are two edges that are not discovered by the discovery graph, x to z and y to z, which gives us a distance of 2. The closer the distance, the closer to the ground truth we are. Alright. There are many different causal discovery models which can find the causal graph using different approaches. And we have provided several examples for your reference as well. And we have summarized how do they work. But for the sake of time, I will directly go into causal effect estimation, which is where we aim to quantify the causal effects between variables given a causal graph. So it means that we have to have a causal graph to begin with. For example, in this graph, if I apply particular treatment on x, what will it be its effect on y? How do you calculate this effect? So we have learned that condition can help us to remove the confounding effects, which we can actually put it to use here. So given this causal graph, we can select a common node as backdoor, which is also the confounder on two variables. So it's going to introduce some noise to our observations, which we do not want, and condition on it. This is called backdoor adjustments. So if you remember that we mentioned condition can be used to block a causal path, we use the blocking to help us to remove the noise and have a connection X to Y without any backdoor intervention. All right. When we quantify causal effects, we have several approaches. Individual treatment effects is one of them. It is when we treat on a single unit. Here, the treatment effect on Emily is -1. We compare two cases where the person is treated and has not been treated, or two different phases. When we aim to understand the average treatment effects of a subgroup that we condition by X, we use conditional average treatment effect. And as you can notice, we condition on the variable on X. And the average treatment effect is the overall effect across the population that is averaged, which is in the name. Similar with the causal discovery task, we have some assumptions for causal effect estimation that help us achieve executing the algorithms, which are stable unit treatment value assumption. It means that there is no interference among units. In other words, a treatment gives the same outcome under the same conditions. There is no unknowns. Social networks are a violation of this because interaction between treated groups can cause a spillover effect. So this is something we should be wary of. Positivity is we have to have samples in both control and treated groups, because if we have only a single group, then the data would be biased. And unconfoundedness is also known as ignorability, means that all confounders are unobserved, meaning observed. It means that there is no unmeasured confounders that can affect the system. An example algorithm on this would be a meta-learner or a T-learner. It is essentially where we utilize multiple effects, multiple treatments, or given any treatment effects like ITE or CATE or average treatment effects. And this allows us to have a complete flexibility on the choice of models because we can apply this to any algorithm, actually. The first part is we choose any kind of regression model. It can be a linear model, random forest, or neural network. And then we split the training data by treatment with a treatment T. And where the treatment is 1, we fit a specific function, and when the treatment is 0, we fit a separate function for it as well. And on the test set, we create 2 copies of testing data sets with the same confounders, set T1 in one copy and 0 in the other. And we use the treatment 1 trained model to predict if the treatment has been made or not, and Y0 to predict T0. And that is how a T-learner works very briefly. All right. Before talking about how do we evaluate the performance of these models, we have to address a certain issue. So, quantifying the causal effects is very much easier to do on synthetic data because in synthetic data we have control over the effect's value, the quantity of the effects. However, on the real world data, we often assume the test set is balanced across treatment groups. So we can only approximate the comparisons. And the individual treatment effects is another problem because when we treat on an individual, we cannot have 2 different cases for an individual. A person cannot be healthy and sick at the same time. So direct evaluation of individual treatment effects is sadly impossible in the real world data, unless we have complete twins, which is a digital twin, which is not real world data. All right. Another metric that we can use, is an uplift curve, which visually represents the causal effect of a treatment on an outcome of different segments of groups, which can be used as a metric. And there are other causal effect models that work with different approaches. For example, matching mimics a randomized experiments by balancing covariates, or causal forests use tree-based method that learns how to do treatment effects vary across individuals. All right. To recap how causal discovery and causal effect estimation method works, we provided a set of causal discovery algorithms and causal effect estimation algorithms, and there are also different public available resources that utilize these models or do causal discovery or effect estimation. Do-Y is one of the most known ones, EcoNML, CausalLearn is one of them, and CausalBench is a contender in this field. And we also provide you with a set of references that we utilize through this session. And that's pretty much it for causality. Now, before we get into the actual hands-on part, do we have any questions? All right, thank you. Now I will leave the stage to Pratanu.
Thank you, everyone. Thank you, Abhinav, for the opportunity. So now let us actually get into how to use CausalBench and understanding the framework in greater detail. So I highly encourage you to please follow along. So for this, the first thing that we need is please visit the tutorial.causalbench.org. And once you open this particular website, what you can see is that if you scroll down, you will have this quick start file, which is a Google Colab file, which we're using for the purpose of this demonstration. And please open that file. It will lead you to a Google Colab notebook and make a copy. So just click on File and then Save a Copy in Drive. Now, we have done this so that it is easy for you to follow along. If you don't want to use Google Colab and directly get like dirty with bare metal, you can do that. You can install your own Python version and just install the Python packages that we are doing. Now, the first thing that we want to do here is that we want to install the CausalBench ASU Python package, which is the main entry point to building experiments, building benchmarks, and executing them. And we have the requirement, of course, is that we need Python 3.10 or greater. And also for the purpose of this tutorial, we will be using the gcastle library because some of the models that we are going to showcase internally use some other Python libraries, and that's perfectly fine. The main aim is that we create models, data sets, metrics that are easily, like very modular and easy to use. You can plug in, you can easily swap out a particular causal learning model with something else. So getting started, we first install the CausalBench ASU Python package. And for that, please execute the first cell. And this particular operation might take a while. It will install a bunch of dependencies and then finally install. And also this restarts the IPython. So it might actually ask you to restart the Google Colab kernel. So we'll wait for that. Yes, so as you can see, we have the restart session notification here. So we'll simply click on restart session and re-execute this cell just for safe measure. In the meantime, while this executes, did anyone have any issues trying to access the Google Colab notebook or trying to execute it? Okay. Great. So we have the CausalBench ASU Python package installed. Now let's go ahead and quickly install the gcasl library as well. And finally, we import the modules for CausalBench. So we have several modules in CausalBench, and we will want to import those. And we'll get to describing these modules in the next section. So before we do that, in order to access the modules or any kind of information that is already published on the CausalBench website, we need to use credentials. We need to use our own credentials. And so we will take this moment to create our own accounts. So if you have not done this already, please go to CausalBench.org, and you can see this is a website for where we store. It acts as a repository as well as our benchmarking information. It shows all the benchmarking information. So simply click on New User and register here, and enter your details, and tick the box and click on Sign Up. Once you do that, you should be getting a verification email. And once you get that verification email, you should be able to log into the CausalBench website. So I already have an account, so I will simply log in and show you what the interface is supposed to look like. Here you go. So we have a bunch of tabs for the different data sets, models, metrics that I have published here. If I untick the show only my content, I can actually see what other people have published as well. Okay. So if anyone new has joined, for them, just go to the tutorial.causalbench.org and scroll down and open the CausalBench tutorial file. And once you do it, make a copy of it. And here we are. So execute the first 3 cells. So you should be able to install the CausalBench ASU Python package and the gcasl library, and finally import these modules. Now resuming the tutorial. So when you first execute CausalBench, you will be needing to enter your credentials. We'll see when that actually comes up. So first, going into describing the different modules that CausalBench is divided into. You have seen this diagram before. So we have the data set, we have the task, first of all, which defines what type of task we are undertaking. For example, CausalBench currently supports the static causal discovery or temporal causal discovery. For the purpose of this demonstration, we'll stick to static causal discovery because that's all the time that it supports. And we have multiple data sets, multiple models, and multiple metrics. And one data set, one model, and all the metrics combined together forms a benchmark scenario, which is the smallest possible unit of execution in CausalBench, and along with a set of hyperparameters which change the behavior of the models or the metrics themselves. And when we execute this benchmark context, we generate a benchmark run. So now, looking at what a data set, or how do we define a data set, right? We are generally packaging data sets, models, metrics as zip files. And internally, we define it through a config file and one or more data files. So taking a look at one of the zip files that we have prepared for you as part of this tutorial. So you can see we have one particular config file. This is the abalone data set that we are working with. And when you take a look at it, what you have here is the name of the data set. So we have a lot of metadata here. We specify the name, the URL, for example, if you want to refer to some source, and you also have a description of this particular data set. And then we have structure of the data files themselves. So we define the structure. So we say, okay, we assign a label to a particular file, calling it file1, for example. We could call it anything else, but it's just a variable name. Let's call it a variable name. And we see that the type of the file is a CSV and it's a data frame. And this is the path to the file. And along with the whether there are headers, how do you refer to those, what is the data type, and what are the different values it can accept, or in case of decimal data types, what are the ranges of values it can accept, and all of that information. And other than that, we have the data files in CausalBench internally supports two specific data types, the spatiotemporal data and spatiotemporal graph. So these data types are designed to be universal for spatiotemporal causal problems. However, we realize that as users, it may be very difficult for you to, or tedious for you to convert all data formats and even unnecessary. So for example, if you just have static data, there's no point for you to manually convert each data set to spatiotemporal data format. Or if you have a static adjacency matrix, you don't want to do that. So we also provide helper functions which can do that for you. So you don't actually have to do the conversions manually. And taking a quick look at the two data formats. So let's look at spatiotemporal data. So taking an example of the sentence that is printed there, rainfall recorded in Tempe on October 25th was 10 millimeter. Here, a tuple in the data format, in the data file would be that rainfall is a sum variate in the data. And for that particular variate, the recorded amount would be 10 millimeter. And the space would be Tempe, because that is where the rainfall occurred. And the time would be October 25th. Note that we have another variable called the target variable. This is nothing but just another variate, but that is something that has been assigned a special index called target. So for example, if we had classification problems, if we had a causal classification task, we could use a specific index called target to refer to what is the target class. Similarly, we have a spatiotemporal graph, and here, let's take the example, rainfall in Tempe causes flood in Gilbert after 1 day. Here, rainfall is my cause, and Tempe is the location of that particular cause. So rainfall occurred in Tempe, and that caused something. So what did it cause? It caused flood. So that flood is the effect, and Gilbert is my location of the effect. Finally, we also have the option to add causal strengths or causal lags. So here we say after 1 day, so we say there is a causal lag of a day. We could also say quantify what amount the effect is, and that would be the causal strength here. So before we go to models, let us now try to actually execute the dataset. Basically, we want to fetch this dataset zip file we have already prepared and publish it. So when you do that, simply hit this execution cell, and it should ask for your credentials. So this is where you enter your own credentials, as I am doing. Once you do that, you should see a message pop up saying, hey, a new dataset has been published with visibility equal to private. So if I go to the CausalBench website now and I refresh, right, I should be, and make sure the show only my content is checked. So if I do that, and I can click on filter and filter by dataset ID, and I actually copy this dataset ID here and I paste it here, and I hit enter, you can see a new dataset has been published, and it has been published by me. As you can see, the uploader has name is present. If you look into your own web version of the website, like when you log in your own account, you should also be able to see that abalone dataset has been published, but with your name. Moving on to models. So a model is defined through a config file and a Python file. Now, the Python file here essentially acts as a wrapper. You can actually create your own, like you can have any things written, programs written in any other language, but you can just use the Python file as a wrapper to call that and then send back the results. And taking a look at the example that we have prepared, we are using the PC algorithm, and we have a zip file for that. So taking a look at the config file here. So the config file provides again some metadata, the name, source, URL, description, along with a task. So a model is intrinsically tied to a task. So we say this is a static causal discovery model, and the paths to the Python file. So it stores the path as well, and any set of hyperparameters. So it calls, there's a hyperparameter called variant, alpha, CI test, and the data types for them, their descriptions, and the default values. So it provides, the model creator can provide some default values for them. And when we take a look at the Python file itself, so the Python file must contain a function signature which is pre-specified for that particular, based on the task. And you can see all about that in the documentation. But essentially it takes, for example, this is a static causal discovery model. So it takes some tabular data, some static data, and the hyperparameters, and an instance of an object called helpers, which is defined in the task, which you can use again for converting stuff. So here the gcastle library, for example, doesn't actually use spatiotemporal data format. It uses simple adjacency matrix. So we provide the task provides ajmat to graph, this function, which you can easily use to convert it to the output to a spatiotemporal graph format to maintain compatibility across CausalBench. And let's quickly go ahead and execute this as well. And anyone having any issues right now? Good. So once you have done that, once you have published the model, you should be able to see, okay, a new model has been published with the module ID 16 and the version 1. So I can go to my models now, maybe refresh the page. And if you see this button, toggle filters, so click on toggle filters and click on model ID. I simply search for model ID 16, and you can see a new model has been published with my name less than a minute ago. If you go into your own accounts and you have run this code, you should be able to see the same, but with your own name. Similarly, a metric is defined with a very similar structure. And right now I'm going a bit quick given that the time, but we can definitely discuss more on how to play around with it. But here is we are looking at the accuracy metric for static causal graphs. And we, again, have a very similar structure with hyperparameters and all the metadata. But what changes in case of a metric is that in the metric, the function signature changes, because here the inputs and the outputs are different. So here in metric, for example, it takes two inputs, two major inputs, the prediction and the ground truth. So the prediction and the ground truth are basically the predicted causal graph and the ground truth causal graph, along with hyperparameters and helpers again. So all of this is used to essentially output a score denoting what was the accuracy between the predicted causal graph compared to the ground truth causal graph. And similarly, when we execute this as well, should be able to see that, okay, a metric has been published with the module ID 20. And I can just simply go here. And you can see that a metric with module ID 20 has been published, and it was uploaded by me less than a minute ago. Great. Any issues so far? Cool. Now we finally come to the benchmark context, right? So the benchmark context essentially encapsulates the data sets, models, metrics that we just now created in order to actually build a unit of execution. And then we'll finally execute this to produce a benchmark run. So we can directly create a config file, because that is what it consists of. It just consists of a single config file. But instead of doing that, we realize that you may not create data sets, models, or metrics every day, but a benchmark context is something that is very frequent, because you want to build different contexts with different data sets, models, and metrics and execute it. So we provide a code-based way where you can simply do context.create, enter a task like discover.static, and then you see you mention the name of this particular context and the description along with the data set. So we already have the instance of the data set 1. And this is essentially mapping a data set. So data sets, remember, are independent of the task themselves because data sets can be used for all kinds of purposes. So we intentionally kept it separate from the task. So what you need to do here is map the data files to the inputs of the task itself. So for example, the static causal discovery takes 2 inputs, data and ground truth. So we pass the file, associate the file labels to the data and the ground truth, and also the model and their hyperparameter. So we have the model along with the hyperparameter mapping in case we want to override. For metric 1, you see I have kept this intentionally blank because I actually don't want to override the hyperparameters. I'll just use the default. So if you can just leave it empty. And once you do that, you can actually execute, right now we are publishing, and you can see a new benchmark context has been published with module ID 26. And I can go to benchmark context and filter by the context ID 26. And this will show all the information. So it was published by me, and you can see the dataset ID. You can go to the dataset itself, reference to the dataset itself. You can see the models and their hyperparameter values, and also the metric and their hyperparameter values. So the default hyperparameter for alpha is 0.05, but we actually here, just to demonstrate, we use 0.1 instead, and you can use some other value as well. And once we have created this benchmark context, now let us actually try to execute these benchmark context to produce a benchmark run. So first, before that, let's understand what is a benchmark run. So a benchmark run, again, consists of a config file which essentially profiles all this information. So what information does a benchmark run profile? It profiles information about the benchmark context reference. So it contains the ID and version of the benchmark context. Also, it contains the platform information. So it documents the operating system, the CPU, the GPU, the memory, means the actual physical things on the system, essentially, the setup of the system. It also contains the scenarios. So it details what are the benchmark scenarios. So it contains the data set, the model and metric pairings, along with any kind of outputs that the metrics generated or the data models generated, and the profiling information. So this profiling information means the execution time that it took, any kind of hardware utilization. So how much CPU was utilized, how much GPU was utilized, all of that information. And also the software packages that were used. For example, if a particular model is using GCastle, it will note that it uses GCastle based on actual usage and not based on the imports, but on the actual usages, and also the version of those and the Python library and all of that. So let us quickly go ahead and run the benchmark context itself. And when you have, this might take a minute or two. So in that time, anyone, if you are facing any difficulties executing it, please let me know. Okay, so this has executed the benchmark run. So if you print the output of the benchmark run, you should be able to see that it only contains one scenario, which is abalone dataset with the PC model and the hyperparameters as specified. They are shown here, and also the metrics output. So it says the output accuracy here is 0.6. Now, finally, I can go ahead and publish this on the CausalBench website, and you can see a new run has been published with the module ID 99. So if I go to the runs page and make sure you select, untick this box so you actually see the runs, you can see the latest run 95 has been published here, which is your run. You can actually click on it and see that, okay, abalone dataset PC accuracy static, and the result was 0.6, and it was executed less than a minute ago. You can see more detailed profiling information from here, we plan to add more visual components to CausalBench to actually showcase this directly in the UI. But for your own information, if you want to actually see more details in more depth, you can see what CausalBench version was used to produce this particular run. What is the context that was used for producing it, the task involved, and also the time that it took to actually execute this particular, and all of this is in nanoseconds, and the profiling information. So basically, what was the platform? It was a Linux system with kernel 6.1, 64-bit architecture. We can also see the CPU, the GPU, and the total amount of GPU memory, the driver the GPU used, the disk, and here if you're executing through Google Colab instead of your local system, it might be a bit, you won't be able to see the disk details because Google Colab does not report many of the disk information as it uses an ephemeral disk. But you should also be able to see the total amount of RAM and the total amount of storage space on the system. And now looking at the scenario, line number 12 here, you should be able to see that, okay, it consists of one data set, one model. It puts the output of the model and also the time it took to execute just the model. Its profiling information such as the amount of memory used, the amount of GPU you use. So here you can see GPU utilization was 0, which is expected because our particular model here, the PC model, does not rely, its implementation does not rely on the GPU at all. And we can also see the disk usage. So we say that, okay, it read this amount of bytes and around 15, this amount of bytes it has written, and the Python version and the imports. And finally, we see the hyperparameters. And same for metrics, we see the output score and the time it took to execute and all of this profiling information. So for example, in metrics, you can see it reports NumPy because it doesn't actually use gcasl, but uses NumPy instead. And this actually brings us to the first scenario of that we wanted to demonstrate. But this is one of the ways of creating a benchmark context. We also have a way of creating a benchmark context using a GUI, which we will look into further detail after the coffee break. Before we go to the coffee break, if you have any questions, please feel free to ask now, but we'll also be available during the coffee break. When we return, we will proceed with looking at the GUI-based way of creating benchmark context, and then do a further deep dive into seeing how we can utilize models or metrics that someone else has already published, and creating or publishing public benchmark executions, benchmark runs, and seeing, okay, how do we use all of this benchmark result information for causal analysis and causal recommendations, so causal explanation basically. So we want to draw insights from these results themselves. So we will look, and this platform gives a unique opportunity to do that. For example, as Abhinav has already mentioned before, trying to answer questions such as how does a particular hyperparameter affect the output, how does a particular CPU affect the execution time. So all of these questions can be answered, and we'll showcase some of those capabilities as well. Any questions? Okay. In that case, have a good coffee break, and we hope to see you back at 10 a.m.
Okay, let's start the second part of the tutorial. Welcome back, guys, from the break. Before we move ahead, I'd like to again give everyone a recap on what we discussed in the first part of the session. So we discussed what CausalBench is and our goals for that. I'll repeat them again. So we want to promote universal adoption of standardized datasets, models, and metrics for causal learning. And we want to facilitate research, collaboration, and promote trustable and reproducible benchmarking. We also want to promote fair and flexible comparison of methodologies in causal learning. We went through different scenarios where you can use causal bench. The first one being you are a data set or basically a resource contributor. You want to share your resources with the community. So you upload your resources to CausalBench. And we also discussed how CausalBench supports users in doing this. We have features that allow you to keep your resources public or you can keep them private, but still you can experiment even with the private resources. We allow you to modify resources of other users and publish a copy of your own in case you choose to do so. And then in the second scenario, we discussed how you can use CausalBench to explore resources that are already available, and we mentioned that we provide powerful filters and search options for you to do this exploration. And in the third scenario, we talked about the benchmark executor, which is kind of the core of CausalBench, where we discussed how users can replicate experiments and also create experiments of their own. We will get into detail about how you can replicate experiments in the current part of the tutorial. We also presented the sample benchmark context output. We mentioned that we profile various software and hardware parameters of the benchmark context run. And we also mentioned that we index all the public benchmark runs to Zenodo, which is beneficial to the users because it provides a DOI which is permanently indexed on Zenodo and citable. And the last scenario included that of a benchmark explorer who essentially explores the runs already published to CausalBench, and the aim of such a user is to analyze the experiments that are already being run in the community, see where they can improve I don't know, the accuracy metrics or even the hardware usage, make the models efficient in both these categories. And we also discussed how causal explanation module of CausalBench can support this endeavor of users. With that, I want to conclude the recap of CausalBench and go over what we learned about causal learning. So causal learning essentially answers the question of why, which is very important, and it establishes a relationship between the cause and an effect. We discussed two questions. One is causal discovery and the other is causal effect estimation. Causal discovery essentially establishes the cause, what the cause is and what the effect is, and cause effect estimation estimates the effect of the exact effect. It's basically not just enough to know that vaccine affects a patient's health. It is also important to know how a vaccine affects a patient's health. For example, it could affect the effect can be negative or positive essentially. In this case, hopefully it's usually positive. And then for the hands-on part, we discuss how you can create and publish datasets, models, metrics onto CausalBench. Essentially, how you can publish resources onto CausalBench, how you can execute benchmark contexts. We also generated and published benchmark run, and then we went through the file, the config file of the benchmark run, which had all the profiling information and the metric results. After that, we explored the published modules on the CausalBench website. For the rest of the tutorial, we will explore the other benchmarks which are already published onto CausalBench. We will reproduce the experiments, some of the experiments which are published onto CausalBench, and after that, we will use causal explanation module to gain further insights into some of the experiments that were published onto CausalBench, and then we'll go over what the plans we have for CausalBench in the future. With that, we'll move on to the benchmarking.
Thank you, Abhinav. We shall now get back to the benchmarking part of CausalBench with a hands-on approach. And since we are, I think we are all familiar faces, so I skip the recap and directly move into the CausalBench designer. So before the break, we had promised that we would show you a way to design benchmark contexts directly from the UI instead of trying to create the benchmark context using the code itself. So let's get into that. So for that, first go to the CausalBench.org and log in with your credentials. And once you do that, what it provides here is you can go to Context tab and click on Design New Context. So once you click on the Design New Context, you come to a page where you are actually able to see there are data sets, models, metrics, essentially the same structure as a benchmark context. And the internet is probably a bit slow. That's why we are still seeing it's loading data sets. So just give it a moment. So what this provides you with is essentially a zero coding environment to kind of plug and play different models, metrics, and data sets for any for users from any any background without actually having to write a lot of code. And that is especially useful since, let's say, I am a data set expert. Okay, I'm working in this particular field, and I want to get into CausalBench and explore some causal models, try to use them effectively. I can do that very easily here. So the first step here, of course, is selecting a task. So I say, please select a task, and I use discovery.static. And once I do that, I click on add a data set. Once I add a data set, I can select a data set by ID. Sure. I can go back. So in order to go there, you go to CausalBench.org, right? So just log into CausalBench.org and go to the Contexts tab. Yeah, you have to go to Contexts first and then click on Design New Context. Okay. And after that, you open this page, you select the discovery.static and click on Add Dataset. And we'll be using this we'll be creating this benchmark context. So we select static causal discovery and then select the abalone dataset. So from the ID, from the drop-down list, I select one abalone. This is the ID one. So we select one, and the version is also one. So we only have a particular version for the abalone dataset. And after that, we can see all the details, the name, the description of the dataset, the person who uploaded it, the visibility, and also the URL and timestamp. Notice that here the visibility says public. And what this means is if I go to the CausalBench, and this has been published by Ahmet, as you can see, but if I go to show only my content and disable it, and I search for a data set with model ID 1, you see I can still see it and it says the uploader is Ahmet. But if I were doing show only my content, this wouldn't have showed up. You can see it doesn't show up because I did not publish it. So essentially, we are now getting into trying to use the data sets, models, and metrics that someone else has published. So for that, need to create a dataset file mapping. So we select the dataset file. So here we are going to select abalone mixed static CSV file. So once we do, and we select the ground truth file, and here we are selecting the adjacency matrix file 2. We do that and we click on apply. Make sure to do that you do click on apply, because if you don't, it might not save the changes. Once you have done that, you can see we have added a new data set. Now we do realize that even this might be a bit tedious in the sense that this drop-down list might not be the best scenario for you. So what we do provide is also a unified search here, where you can select, simply search for the data set or model or metric. So you can see here the data set, it says SACS, which is also a very famous data set in causal learning. And we simply search for SACS, and you're going to see a data set shows up with the ID 1443. I select it, and it automatically selects the latest version. And you can see all of this information has been populated, all the metadata has been populated here. And I select a particular, I also map the files themselves. So I select the data file and the ground truth file, the adjacency matrix, and I click on apply. For the models we are going to use for this particular experiment is our PC and GS. So let's start with GS. I search for the GS model, and once I click on it, it populates. You can see it still selects the latest version. You could obviously use an older version, but I recommend sticking to the latest one because they probably have some bug fixes as usual. And you can see that, okay, we have the description, uploader, all the metadata, but at the bottom you now see a hyperparameter configuration. So either I can leave it blank, or I can actually add a configuration and override the defaults. If I don't specify anything and just click on apply, it will automatically take the default values. Let's now try to add the PC model. Same, just search for PC and add it. Once you do that, you can see that at the bottom, again, the hyperparameter configurations. Let me try to add a hyperparameter configuration this time, right? So you can see when I click on add configuration button, I have the variant, the alpha, and the CI test. These are three of the parameters, hyperparameters that PC algorithm takes. Let's try modifying the alpha parameter. So the default is 0.05, but I want to use 0.01. If you want, this is a significance level of the condition independent tests, independence tests. You can actually try with a different value instead of 0.01. You don't exactly have to follow me. You can try let's say 0.02 or whatever. And once you do that, you click on apply, and you can see that the PC model has been added as well. Finally, let's add 5 different metrics. So for this, let's try to add accuracy. And we search for accuracy, and you can see there are 2 different versions, accuracy static and accuracy temporal. Please make sure to select the static version variant, because that is what we are doing. It's the discovery static. After that, let's select the precision. So same, we search for precision, and we add the precision static. Recall. So this is going to be very simple. You can see recall has also been added. F1 score, so I simply search for F1, and you can see there's F1 static, which is what I select, and I have the F1 static populated as well. And finally, the structure and Hamming distance. So the model publisher has actually named it SHD, the short form of it. So just search for SHD, and you'll see SHD static. And finally, that actually builds our benchmark context. We actually come to, we have the layout for it. It's a graphical way of doing it. Anyone has any issues following till now? Okay. So now, finally, let us export this context. So we click on export context. You can see we have a task type and the name and description and the items to export. You can see it says we're exporting 2 data sets, 2 models, and 5 metrics. That's fine. Let's try to name it something reasonable. I will call it tutorial static causal discovery. And I'll call it scenario 2. Great. So that's what I did. And put anything here and just click on export. And once you do that, you can see a context export.py file has been generated. So this py file, what it does is it essentially creates that code that you need to execute to create this context and publish it and execute it. Sorry. Now we already have these lines. We already had imported the CausalBench module, so we won't need them. But what I want you to do is once you have this exported Python file, copy this context information, and let's go back to the file, the Google Colab notebook. Again, for many of you, if this has disconnected, please click on reconnect. It might actually might have removed your CausalBench ASU Python package installation. So if it has, as you can see for me, it has done that. So I will simply reinstall I'll reconnect to the environment and reinstall the CausalBench ASU Python package. This is not something that you need to do if you're running it on your own system. This is just a Google Colab thing. And once you do that, also make sure to reinstall gcastle and import the modules again. We'll just give it a brief moment to finish. Great. So once that is finished, we will hide the scenario 1 because we have already gone through that. Now in the scenario 2, let's copy the code that we generated using the designer into this particular box here. And once I do that, I can simply click on execute. And for me, it asks my credentials again because the environment is essentially closed. And once I do that, now it is fetching the data sets, the models, the metrics, everything from the CausalBench website, and then building a benchmark context out of it and then executing it. So as you can see, it is very easy to tie in all of the different components created by different users because of the standardized way of doing things. And this usually takes around a minute or two. So please let me know if you face any issues by then. Great. So once it has executed, you can see that the outputs are being displayed. So we see now 4 scenarios. So remember, since in this designer we have 2 models and two data sets and 2 models, it creates actually 4 scenarios. So one model, the Abalone GES, Abalone PC, SAX GES, and SAX PC. And so that is what we see in the output as well. So we see Abalone and GES with different hyperparameter settings and all the output values, the output scores. And we see the same for PC as well. But do note that here in the PC, the alpha hyperparameter has been 0.01. That is what we had set. If you had set a different value here, you should be also able to see that different value reflected. And similarly, we have output for SAX with GS and SAX with the PC module. Moving on, we now know how to use other people's data sets, models, and metrics. Now, how do we execute someone else's benchmark context, right? So if I'm a benchmark context executor, I might want to reproduce someone else's experiments. So what that means is a major goal here is that if you claim that, hey, I have run this particular experiment, or this benchmark, and I got these results, how do I verify them, right? So for that, CausalBench provides reproducibility. So if you look at the scenario 3, the scenario that I just demonstrated, that we just created, I have already prepared that same exact scenario before, and you can go to benchmark contexts and take a look at the context ID 19 here. And if you look at benchmark context 19 version 1, you should be able to see that, okay, we have the SACS and abalone data set along with GES and PC, and I have also modified the hyperparameter here. And all the metrics that we just discussed have also been added. So I can simply, instead of passing a zip file, use a module ID 19 and version 1. And once I do that, I can simply hit execute. And you will see that, okay, fetched context with module ID 19 and version 1. When I actually click on execute, it will do a lazy loading. So it will lazily fetch all the models, metrics, and everything, and it will execute again. Right? I mean, assuming that this is a new context, this is what it will execute. And once it does this execution, now I can actually print the run, and then I can publish it to the public. So everyone else can actually go ahead and see it. Now, once this is done, so again, this will probably take a minute or two. Any issues till now? No? Okay. Fine. So once this is run, again, you can see the same outputs because essentially we have executed the same context, but I have prepared it instead of you. And once you have these results, now notice I said run to.publish, public equal to true. So what this does is it will try to publish it as to the public. Now, publishing to the public is a permanent operation. You cannot just like revert it once you publish it to the public. So you see, are you sure you want to publish it to the public? Simply enter Y and press enter. And once you do that, this publishing to the public usually takes a bit more time than the other publishings because this is doing a lot of stuff in the background. So while it does that, let's quickly go and take a look at the next goal of CausalBench, which is transparency. And what it does is it provides a provenance of the public benchmark runs. So the target here is four-pronged. What it does is it must be complete, essentially saying that all the information collected that is possible to collect during the benchmarking is collected and stored. It is available, meaning that anyone who should be able to access and cite these public benchmark runs. It should be permanent, saying that it should always be available once it has been made public, and you should not be able to retract it. And it should be immutable. That is, once you have made a change, once you have published them, you should not be able to go ahead later and correct mistakes. You can always publish a new one and say that, hey, this is the new version of it, but you shouldn't, your profile, your footprint should always remain. And so that is the goal here. And for this purpose, we utilize the Zenodo, which is a document object identifier provider. And all public benchmark runs, all the results and profiling information that, as we have already demonstrated before, are collected and stored. And they are actually stored on Zenodo as well, which is a third-party platform. So it is independent from CausalBench. And a digital object identifier is assigned. So as you can see, we have this public benchmark right now. So if I go back and go to my runs, I should be able to see that run 102 has been created by David. So you can see that I can see other people's contents here as well. Yeah, just let me show only my content. I think the internet is a fair bit slow, which takes a bit of time. Yes. So as you can see, I can see my benchmark run. Yeah, the request is probably taking time to load. Okay, this is taking a bit of time to load because of the internet issue. But in any case, you should be able to see, yes, now you can see that a lot of the benchmark runs have been populated. Okay. Yeah, the internet is really bad. Yes, now you can. So you can see that all of your benchmark runs are visible here right now. I can see all of them over here, and that's great. That means it is working. And when I click on one of them, I can actually go to Open DOI. And when I do that, you can see it leads me to Zenodo. And what here Zenodo provides me are for three things. It creates a digital object identifier. So you can see I am assigned a Zenodo identifier, and this cannot be changed. You can, of course, publish a new version, but this cannot be changed. Second, what it provides me with, this is not the system. Yeah. And second, what it provides me is an immutable URL. So this URL remains constant all the time. And finally, we have this can be cited in any future research, and it contains all of this profiling information. So if I get the same YML file here attached as a digital footprint, so it records what CausalBench version was used, what is the context version, and the profiling information. All of this, which we have seen before, all of it is recorded in this particular file. And with that, I hand over the platform to Ahmet, who is going to lead you through the CausalBench explanation and recommendation.
Thank you. So, as you have seen, CausalBench is one of its strongest points is that we have a public repository of benchmarks, meaning that anything that is published on CausalBench to public is accessible by everyone. And it is one of the core values of research. We have to move iteratively. And without accessing the resources of other people with ease, it is going to be difficult. And that is what we solve with the CausalBench's repositories. But we can actually achieve more because at this point, we have tons of different benchmark executions at our disposal, meaning that we have around thousands of different executions. All of them are in the single format, which have datasets, models, metrics, and hyperparameters. So, in a way, this is also a dataset. And we can say that how can we extract causal information from the benchmarks? So in a way, we are doing causal learning on the causal learning algorithms. So the questions that we can ask to this data is that, hey, I got this benchmark results, or my result took this much time. How did my CPU affect? How did my GPU affect? Or how did the resource I have used affected the results I got? Which we record everything in CausalBench. And causal explanation feature attempts to answer this question. So, as I said, we are applying causal learning on causal learning algorithms. But as I have said before, we need a causal graph for this, because if we want to estimate the effects of which affects which one, we need a causal graph. So, how do we get the causal graph? We either want to do a causal discovery or two, contact experts. Thankfully, we have the domain knowledge for this. So we have provided you with a causal graph of a benchmark in CausalBench. So this graph that you see is actually our backbone of our explain feature. And we represented everything that we do in a benchmark study, from the datasets, models, metrics, the software or the system configuration, and their effects over system usage metrics, accuracy metrics, and time metrics. Given this causal graph, we can estimate or rank which edges are strongest among this representation. And it is what we achieve with causal explain feature. In a way, we provide the causal graph, we provide the data, and then using the explanation feature, we receive a report. So actually this is something we are going to do in a couple minutes. And the goal here, or the output, is over a selected measure, for example, on this example, it's time duration, which variables have the causal effects, or the quantified causal effects over time. So causal explanations by themselves aren't insight enough, but hey, like we are aim to provide like transparent and explainable benchmarks. Why should not we utilize this information that we have to provide more causally meaningful experiments? As CausalBench, we have taken that step ahead as well, and we have utilized this information to recommend additional benchmarks. So at this point, with the causal explanation, we know that a particular case or effect has more effect on the target variable. And if we explore this cause, we may learn more. And those goals create the basis of our causal recommendation feature. Essentially, by representing selected experiments that I have just shown, and their selected hyperparameter configurations in an n-dimensional space, we can define two sets. One of them is the explored experiment sets, which are the experiments that have been done on CausalBench, that are already explored. And the rest of the space is the unexplored space, where more experiments are needed to understand or observe the potential effects within a benchmark context. And our goal is to provide the users with this unexplored experiments or the benchmarks, so that the benchmark set in the end of your study is well explored, which is a key point. And by utilizing the results from causal explanation, we recommend experiments with a weight on the selected causes. So for example, on this example, on the left, you see that hyperparameter max conditions dimension. Hyperparameter has an effect of strength of 4.5, or the alpha, which is not shown here at this list, but it has a different strength. So we arrange the recommended experiments with respect to their strength. The stronger they are, the more experiments we try to observe. However, one small note though, the variables that you see here, most of them are like model read bys, GPU, or hardware configurations. These are not easily changeable settings on a system. So instead of recommending those, currently we only recommend experiments where you can execute them easily. Because if we had asked you to change your motherboard, yes, that would be a costly suggestion. All right, now let's do the last hands-on part. Utilize CausalBench to causal explain and recommend new benchmarks. For this, please log into CausalBench's website. Pratanu, if you could help me with this. And at the CausalBench's website, please click on the runs. No, you can make it simple. And please use the filter function on the top right, toggle filters. Context ID, use context ID 10, and context version 2. So after this filter, you should see the new results. It will take a second because I believe it has around 6,000 different executions. This is an experiment that we have run before to show you the capabilities of CausalBench, and we did not want you to execute 6,000 experiments now due to time limitations. We can still continue the explanation. Okay, so as you can see, we are able to see the hyperparameters that are possible. So in this case, since we have been working on the PCM-C+, as you should be able to see it, we are going to change alpha and maxconsdim hyperparameters. Let's say that these are the hyperparameters that we want to explore the space on. So we provide what does the hyperparameter represent for your own information. So I will provide 0.1, 0.8, and for maxconsdim I will just use 5, 1, and 50. And after selecting the desired hyperparameters for my exploration, I click on Analyze, which you should get a notification from CausalBench saying your request has been sent, which will be processed, and you will receive an email shortly. The goal for this is, since there can be thousands of experiments, it would not be fair to make you wait in front of concrete or keep the browser on. So this works on a ad hoc manner. Whenever the request is complete, you will receive an email from CausalBench, which also might take a while because of the internet issue Pratanu. But you should receive an email from CausalBench with a result. With a report, sorry. So when you explore the report, you will see that it gives a summary on time duration, that it has run through 6,000 experiments. And this is what it has found. The hardware memory total has the largest strength, CPU, single core, multi-core, so these are all hardware. Then the model differences make the changes. But lastly, we can see that hyperparameters also contribute to changes. In this case, max conditions dimension has a larger effect than alpha. So with this analysis or explanation results, if you could go below, yes, we recommend a set of hyperparameter configurations that you can test. So we are saying that, hey, you have not tested these hyperparameter combinations, and these fill the causal space, what you have chosen. And we also provide you with a number of run IDs and filters applied for your future reference as well. And that is pretty much how causal experiment recommendation feature. In the end, we provide you with causally informed experiment suggestions. This is all for making your benchmarking more robust. All right. No problem. So this was the last hands-on practice. Do you have any questions up until this point? Okay. So on CausalBench, we have already talked about what CausalBench is. Now let's talk about what CausalBench will be, or what are our plans with it. So up until now, our efforts have been concentrated on going public, which we have just done very recently. We have been open sourced. We are trying to do workshops. We are trying to create a community on causal researchers, or just with the general community as well. This KDD tutorial is a part of it, and we aim to do more workshops in the future as well. And the end goal is to let everybody benefit from CausalBench, because as you have seen, we are trying to solve the problems that are existing in the world of not just causal research, in general research as well. With what we are solving with CausalBench is that you don't have to read several papers anymore to find their own experiments or replicate them. With CausalBench, with just a single click, you can copy someone else's work. This can also be a full paper approach as well. So this is what we are trying to do, and this resource is utilized the best if the community itself is involved. So the community is in the center of it. And the last part is actually you. If you have any suggestions on what would you like to see on CausalBench, please feel free to do so right now or through email. That's absolutely fine. But we certainly want you to be a part of it, because with people, CausalBench will prosper. And coming to conclusions. So during this tutorial, we have talked about the problems in benchmarking, what is wrong with our current states, what are the hurdles that researchers currently have to face, and the goals with CausalBench, the motivation of CausalBench. Then we have talked about what causality is to explain the basis, the groundwork on how CausalBench works. Then we have talked about CausalBench with several different scenarios to showcase how you can benefit from it. And we have talked about how to make benchmarking itself better, to analyze it, to improve it, or to recommend it. And that is the end of CausalBench tutorial at KDD'25. Thank you very much. We have provided you with several QR codes. If you want to use CausalBench, we have the application. If you want to learn about how to use CausalBench or learn the tutorial resources, we have the tutorial QR codes. If you want to contribute to CausalBench in the code or in the repositories, or if you want to learn the API, then we have a documentation process. Alright, any further questions, any feedbacks, anything that you want to mention? Because this is the main time where you will get to communicate with the developers of CausalBench. Alright, I mean, we still have a bit more time, so we can spend time any way that you want. If there's anything that you want to explore or ask about CausalBench, we can also provide it. In my opinion, I would like to showcase you the models, metrics, and context that we have, because these are actually the backbone of what we have. And when you want to contribute to CausalBench, this is the first way that you should check. Because we already, for example, we already have implemented our several causal models. Now we have multiple PC models, which will probably created as a part of this tutorial. We will probably need to do some cleanup afterwards, but this shows your execution potential with CausalBench, meaning that if you want to use it, these are the resources available to you. If you want to contribute, these resources are available to you, so you don't need to implement these as well. But you can always have your implementation, have your own version for your own use case. That is pretty much it. Thank you very much for your time. Thank you very much for your patience. If you have any questions, please feel free to contact us. Thank you.